In this chapter now, we will talk about the synthesis of alkenes. So most of the alkene synthesis we've done before in elimination reactions. So a little bit, it'll be a review, but there's still something new, of course. So first of all the synthesis of alkenes that we will talk about here are elimination reactions. There is another one that we will talk about, but that will come in alkynes, so I will leave that for then. But for now, the two reactions that we will talk about are dehydrohalogenation. D meaning getting rid of something. Hydro is for hydrogen. Halogenation is, of course, halogen. So dehydrohalogenation, which means getting rid of a hydrogen and a halogen, okay, which we have done in the elimination reaction. And the other one is dehydration. Again, D is removing and hydration is water. Okay, so you're removing water in this case. So these are the two reactions we will talk about. We've talked about SiteSaves products before in eliminations. And so we will review that again, SiteSaves products and Hoffman product, which is also the non-SiteSaves product. Remember, SiteSaves product is predominant for the more substituted alkene. And then we also will review anti-periplanar, just in case we've forgotten about this, but this again is very specific for cyclic compounds. A lot more for cyclic than for straight chain, but still conformations are important, okay? And then we will also address the whole concept of rearrangement again. So we will do all sorts of mechanisms, okay, to cover rearrangement. So first, dehydrohalogenation. Yet again, these are elimination reactions, and so we've done this before with E1 and E2 mechanisms. Reactions generally are going to be by E2 mechanism and not E1. As we talked about back in E1 and elimination and substitution chapter, that elimination 1 or E1 and SN1, they highly compete with each other, and they're not really very good reactions, okay, as far as the product is concerned or the efficacy of the reaction is concerned. So most of the reactions that we talk about for elimination are going to be by E2 mechanism, and E2 mechanism is favored by having a secondary or tertiary halide. If it's primary, then you might end up getting substitution, okay, and so secondary halides are pretty good for this, so that the halide that has to go away is a little bit inaccessible, okay, and so therefore elimination is preferred in those cases. And the bases that we will use in these ones have to be strong, first of all, and second, it's even better if you have a large bulky base, okay, because the bulky base will not be able to access the electrophile. So in those cases, elimination is preferred, okay, and so this is the general mechanism right here shown in the reaction. And in the reaction here, you can see the E2 mechanism. Everything happens in one step, okay, where we have the base coming to grab the hydrogen leaving its electrons between the carbon-carbon bond, and then the halogen leaving. All right, so all of this happens in one step in E2 mechanism. So let's talk about SiteSaves rule now, which is one of the things about elimination reaction. And remember, SiteSaves rule is when you form the more stable alkene, which is the more substituted alkene. So here's a little bit of a review where you have, here is your leaving group, okay, and then here you have the beta hydrogens, okay, this is the alpha carbon, so these are the beta carbons, and on the beta carbons you have the beta hydrogens. And so here are the hydrogens. Now remember, this hydrogen over here, number B, and this methyl group down here, these two hydrogens are equivalent, so we don't have to work with both of them. We can just do one of them and it'll give us the same product. And then we have this hydrogen, which is different, okay, from this one over at B. So A and B, two different beta hydrogens. So once you do the elimination using a base with hydrogen A, then you end up getting product A over here, which gives you a more substituted alkene, which is the SiteSaves product. And then when you use the base to do the elimination and B hydrogen is gone, the hydrogen B is gone, then you end up getting this product, which is less substituted alkene, 2-methyl-1-butene. You will always get the two products. One will be major, one will be minor. And in this case, because we're not really talking about any selectivity or anything like that, then the SiteSaves product is going to be the major product, and the non-SiteSaves, which is also called the Hoffman product, is going to be the minor product. Okay, and so this is what happens with SiteSaves rule. The base is not specified here, but the base here usually is going to be a small base. Okay. But what if you don't want the SiteSaves product? What if you really want the Hoffman product? You don't want the more substituted alkene. You want the less substituted alkene or the terminal alkene. All right. So then what do you do? So in those kind of cases, what you have to do is use a bulky base. Okay, if you use a big enough base, that big bulky base will not be able to access the internal hydrogens. It will be able to access only the outer hydrogens, and therefore you will end up getting a more terminal alkene. So it's not that this one will not form, the SiteSaves product will not form, it will be the minor one. So at least you can control the product a little bit in this case. All right, so SiteSaves rule is where you can form the more stable alkene, and the Hoffman product is when you form the more or the less substituted alkene. Okay, so it's possible to form both depending on what kind of base you use. Then again, another review over here is the anti-coplanar elimination, which is that the hydrogen that is being removed and the leaving group that is going to leave, they should be on the opposite sides. Okay, so when you're looking at it from a straight chain perspective, then they should be in anti-position, okay, to each other. They cannot be on the same side. They have to be on the opposite side, which means that the dihedral angle should be 180 degrees. Okay, and the same thing goes when you have a cyclohexane ring. So your leaving group in this one, remember, has to be axial. It cannot be equatorial. It has to be axial. And then the other hydrogen that is leaving also has to be axial. And that will drive your reaction and that will drive your product. Okay, depending on whether you will get the SiteSaves product or not, then that depends on what kind of hydrogen is available for elimination. So in case of the anti-periplanar, okay, yet again, these reactions actually just give you a little bit more of an example of what we just talked about. So for example, if you have something like neomethyl chloride, trying to do elimination on this, remember the relationship again is between where the leaving group is and where the beta hydrogen is. Okay, so which means that the methyl group on the neomethyl chloride does not really play much role, okay, as to what it will be. The most important thing you're looking for is the relationship between chlorine and the beta carbons. Okay, and so that's what you look for. And if there are axial hydrogens available for the axial chlorine, then you will get elimination of both of them. Okay, which happens in case of the neomethyl because this is cis, and in case of cis, both the groups are going in the same direction. And remember, this group, which is the isopropyl group, has to be equatorial in this case because it's a bulky group. So if this is equatorial, the chlorine becomes axial then, okay, because they're both going down. And so in this case now the hydrogen is axial. There are two axial hydrogens, and therefore you will end up getting two products, okay, in this case. The more stable alkene here is the SiteSaves product because it can be, okay, and it doesn't have to be the least substituted alkene. So there is no driving force over here for the Hoffman product, and so the SiteSaves product is going to be the more prominent product over here. If we are looking for the anti-conformer, okay, then for the methyl chloride, where the relationship between the isopropyl group and the chlorine group is anti to each other, which means that they are opposite to each other, which means one is going down, one is going up, then you're really limited, okay, to what you can have. Because remember, the isopropyl group still has to be the equatorial because it is the bulky group. All right, so this still has to be equatorial, which means that the only place the chlorine can be is going to be then the equatorial position. And we just mentioned that equatorial positions are not very good for the leaving group. They're much better for, if they're in the axial position. So whatever product you end up getting, first of all, is going to be a little bit less because chlorine should be in axial and not in equatorial position. And then, of course, right here, when you look at the beta hydrogens, there is a beta hydrogen available. But the dihedral angle between the chlorine and the hydrogen has to be about 180, okay, which it is not. So in this case, the axial hydrogen is not leaving, the equatorial hydrogen is leaving. And so, which means that this is not really a very good synthesis, okay. It means you will get the product, okay, you will get the Hoffman product in this case, you will never form the SiteSaves product, okay, in this case. But the Hoffman product that you also get is not going to be a very efficient reaction. Okay, it says 100%. 100% means that there is no SiteSaves product. Okay, all that you end up getting is the Hoffman product. However, it doesn't mean that it's 100% yield. Okay, the yield might be very less because chlorine is not in the most acceptable position, okay, for elimination. So you have to watch out for these things when you start working with cyclic compounds, okay, and see the conformation and not forget your conformation rules as to which group should be equatorial and which should be axial. Just because you want something does not mean that you will get it, okay? You have to follow the mechanism of the reaction. Now let's take a look at dehydration. This is also an elimination reaction, but now we're actually dealing with elimination of water. Okay, so which means that we start with alcohols, the OH group, and again it's going to be a 1,2 elimination or an alpha beta elimination where you remove hydrogen and hydroxide, well, OH, alcohol from adjacent carbons to give the alkene. And then, of course, water is released as a small molecule. So first of all, a few pointers over here. Elimination is favored over substitution at higher temperatures. Now remember, in case of alcohols, it's very hard to get substitution because OH group is not a very good leaving group, okay, which means it would be OH minus. So hydroxide is actually not a very good leaving group. So you will typically get elimination. You would also need acids, okay, in order to do elimination reaction for alcohols. Without acid, this is not going to work, okay, and it will take a really long time and sometimes not even work at all. So you do need the acid for it to work, and we'll see in the mechanism why you need the acid for this reaction to happen, but you need the acid. Okay, it's a catalyst for this reaction. And so then the other aspect of dehydration of alcohols is what kind of an alcohol are you using? Do you have a primary, secondary, or a tertiary alcohol? So looking at all these conditions here for the next two reactions that we have. So look at the first one here where you have a primary alcohol and you're using concentrated sulfuric acid at 180 degrees Celsius, okay, and then you get an alkene versus a T-butyl alcohol, which is a tertiary alcohol, and here you're using only 20% sulfuric acid at 85 degrees centigrade, and you are getting still an alkene. So look at the conditions here. Okay, in case of primary alcohol, you were using concentrated sulfuric acid, but in tertiary alcohol, it's only 20%, which means that your conditions are much milder, okay, in the case of the tertiary alcohol. And then, of course, the temperature also is much less, okay, so which means that primary alcohols are much harder to dehydrate than tertiary alcohols. So why does this happen? Of course, this is all based on the mechanism of the reaction, which we will do in a minute, but that's kind of an important thing over here. The last thing that we will talk about in dehydration of alcohols is, of course, the rearrangement, okay, that can happen. Now let's look at the mechanism of the reaction for dehydration. First of all the reaction mechanisms here are going to be E1 mechanism, which is first order elimination. And the acid that we use over here is going to be used as a catalyst, okay, which means that it will be regenerated at the end. And it's needed only in a small quantity, as all catalysts are, okay, needed only in small quantities. So let's look at the first step over here. The alcohol that we are beginning with is a secondary or a tertiary alcohol. Remember, the primary alcohols are not very reactive. They need very harsh conditions. So usually it's not a very good way to start the reaction, okay, with the primary alcohol. So this mechanism or elimination reaction using alcohol is used primarily for secondary or tertiary alcohols. So the first step that we have is where the alcohol will get protonated from the acid. So as it is right here in the first step, we get started with the acid as the catalyst. So once the alcohol is protonated, it ends up giving this OH2 where the oxygen is protonated, the oxonium ion. And remember, in an E1 mechanism, you need to have a leaving group. Okay, so that's the purpose of this step over here, is to make sure that the alcohol is turned into a good leaving group. And the good leaving group here is H2O. So then in the step number 2, we have the H2O, which goes away. All right, that's the leaving group. Remember, OH by itself is not a good leaving group. So it has to get protonated in order to form the H2O, which is now a good leaving group. So step 2, we form the carbocation over here. And once the carbocation is formed, the third step now is where the conjugate base will come in and pick up a proton. Okay, so the conjugate base, remember, this is a strong acid, so which means that the conjugate base is not very strong. However, since this is dehydration going on and you're forming an alkene, uh, this conjugate base is strong enough to pick up the hydrogen, okay, over here as a proton, and then the proton leaves with its electrons behind, giving an alkene. So this is the mechanism for dehydration. And looking at the mechanism, okay, knowing that you form a carbocation, now you can understand why primary alcohols are not very good for this, because if the mechanism is going to be E1, primary alcohols will form a primary carbocation, which is not very stable. Okay, so that's why secondary and tertiary alcohols are preferred for this kind of a reaction. So just to review again, as we talked about in the elimination reactions back in substitution and elimination, is the stability of the carbocations. Okay, so tertiary is more stable than secondary, then primary, and then the methyl cation is the least. Okay, and which is why a primary alcohol will not be very reactive. Okay, so the tertiary alcohols need the mildest conditions because they are the most stable, they form the most stable carbocations, all right? And they're also the fastest reactions for that reason. So a primary alcohol, for example, you can do the reaction with it, but it will give you low yields, it will take a long time, you'll have to reflux it, or you have to heat it for a long time. But tertiary alcohols can work much faster, okay? And so tertiary alcohols are best, okay, to do dehydrations. Does it mean you cannot dehydrate primary alcohols at all? Maybe yes, maybe not. But the thing about all these reactions, as we are learning, is that there is no single one way that is best, okay, for making any product. If one is not working for you, then there is another way to make the product. Okay, so if, for example, if you wanted to use a primary alcohol to give you a terminal alkene, then there is a way to do it. Okay, we are not learning everything in one chapter. It will come later on. So the other part about dehydration reactions is rearrangement. Okay, and the rearrangement occurs because of the formation of the carbocation. And this is especially true when you have a secondary carbocation, because a secondary carbocation can rearrange to form a tertiary carbocation. A tertiary carbocation has no reason to rearrange. Okay, a primary carbocation can rearrange, secondary can, tertiary has no reason. Okay, so you will find these kind of rearrangements only when you form primary or secondary carbocations. So here is an example of 3,3-dimethyl-2-butanol undergoing dehydration. Okay, and so you end up forming two products again, the SiteSaves product and the Hoffman product. Okay, once the first step has taken place, okay, which means that you have protonated the alcohol, and then you have eliminated the alcohol as water, and you form the carbocation. After this, the mechanism or the rearrangement, everything is similar to E1 mechanism that you've done before with the dehydrohalogenation also. It's just the first steps that are different for dehydration reactions. Okay, and after that, both of them are similar. So in a way, it's kind of a repetition, and hopefully you will not think of dehydration as a whole new reaction, okay, to learn. It's only the first two steps that are new to you. So in step number 3 over here, again, the rearrangement can occur because you have a secondary carbocation and the carbon next to it has a methyl group that can shift. Okay, and so once that shifting occurs over here, then you end up forming a tertiary carbocation. Remember, again, the rearrangement will not take place if you're not forming a more stable carbocation. That's the driving force for rearrangements. And then in comes the base, the conjugate base, and picks up the beta protons. And here it shows again that you have two beta protons available, so you will form the two alkenes. Okay, and one of them, which is the SiteSaves product, again, is going to be the more stable alkene, therefore the major product, okay, in this case. So now your products actually look nothing like what you started with. You still have the same number of carbons, but it does not resemble the starting material, okay, and you have to watch out for that and see if rearrangements can actually occur. So here is another example of a rearrangement, okay, and the reason that I have shown you this one over here is because we talked about the fact that in rearrangements you can have a hydride shift, you can have a methyl shift, in some cases you can have even a phenyl shift, okay? So here in this case, even a hydride shift will give you a tertiary carbocation from a secondary to a tertiary carbocation. So the methyl shift we just covered, okay? So the hydride shift is given here. And the other rearrangement that I've given you over here is changing of the ring size. Okay, so sometimes the driving force for forming a tertiary carbocation is so great that even the ring size will change in order to accommodate that. Okay, so here when we form the carbocation in the first step, this carbocation is a secondary one. So now there are 3 carbons available, 1, 2, and 3. Okay, these 3 are available for rearrangement. Okay, so you can shift this one also. You can shift this one or you can shift this one. Okay, these two, by the way, are alike. Okay, they are the same ones. So you can either have a methyl shift or you can have this carbon shift, okay, over here, which means that these electrons are moving over here to form a new bond. And this is kind of how it is represented. Okay, so this is the bond that shifted from this over here to form a new bond, okay, with the carbocation that gave us the tertiary carbocation. So this structure is equivalent to this structure, which, as you can see, looks nothing like what you started with. Okay, and that happens in rearrangements. And then you can have the elimination going on. Now the predominant product is going to be the SiteSaves product. Okay, you can have a minor product for Hoffman, but the major product is still going to be the SiteSaves product. But here you can see that the rearrangement has occurred. You can also have rearrangement of this methyl group, which is not shown here, but yes, that is possible too. So to end this chapter, which really is a very small one because this is synthesis of alkenes, which we've done before, dehydrohalogenations, dehydrations, you need to know the SiteSaves and Hoffman products. You need to still review about the anticoplanar elimination, which means that the hydrogen and the leaving group, they should be as opposite to each other as possible, which means the dihedral angle of 180 degrees is preferred. We have to still go over the stability of carbocation and then of course the rearrangement, okay, of carbocations. And this is it for elimination reactions and forming alkenes. There will be more synthesis, but for now this is it.